Okay, we're going to keep going with chapter 5 in the Changle and Bowles text. That is um, first law for control volumes. This is going to be lecture 11 for us, page 1 of something. And like I said, we'll just keep moving. Okay. So we finished up last time, and I do have some PowerPoint slides, but we'll come back to those. Um, I can just be on the document camera for a minute or two here. We defined in the last video the uh, general equation for first law for steady flow control volume, control volumes, we should say. First law for steady flow control volumes. And what we will normally do is looks like that pen's going to give out on me. What we're normally going to do is we're going to neglect the potential energy. Since the enthalpy value is often larger than the kinetic energy value, which is often much, 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 much larger than the potential energy value. It depends on the system, but often the enthalpy value is going to be in the order of megajoules or kilojoules. The kinetic energy value might be close to the same as the enthalpy, depending on the device. But normally the potential energy difference would be in the order of microjoules compared to joules or kilojoules, maybe even megajoules for these other terms. Not going to impact the third significant figure probably ever, at least not for the devices we're going to look at. We're not going to look at devices the size of, say, a hydroelectric dam that is almost a mile tall or something like that. That's the level you would want to get to consider the potential energy change. So, with that in mind, if we neglect the potential energy change, we can kind of simplify the first law equation we saw last time just a little bit. Add the in, subtract the out, so I could have the rate of heat in, I could have the rate of work in or the power input, plus the sum across that pin's going to give out on me. Next pin. I keep a stack of pins on my desk for this very reason. I write enough, the pins will give out on me after a while. The summation across all the inlets, the rate at which mass is coming in, times the enthalpy plus the kinetic energy. I know if you're watching this right after you've watched lecture 10, the last part of lecture 10, you're like, Steve, we just wrote this. Yeah, we did. But it's okay. It's really important. It's okay to write it another time. And again, we're neglecting the potential energy here. We're assuming that it is negligible. It's there. It's just we're assuming that it's not going to impact our calculations. So this is the heat rate in, the power input, plus the energy of the rate at which energy is brought in by mass coming into the system. And then we're going to subtract all those things going out. Q dot out minus the power output minus the summation across all of the outlets. Everywhere mass is going out, we've got to add up the rate at which energy is being carried out by the mass. We need to know the rate at which mass is flowing out. That's the m dot out multiplied by the enthalpy plus the kinetic energy. That's v squared over 2. And if it's a steady flow system, that sum is going to add up to be 0. That's in minus out equals change, where the change is 0. If you're sitting here looking at this thing, and Steve, why am I using H here? Well, if you're wondering why we're using H, go back and review the last part of lecture 10. That will help you understand why we're using H. Basically, you have an internal energy plus you're pushing the fluid downstream with pressure. Pressure's not energy, so I need PV. U plus PV makes H, and very quickly. A general simple way to think about that is for control volumes, I'm going to use H's when I'm describing the energy of mass that's flowing. If I'm dealing with a closed system, I'm going to use internal energy because that mass is not necessarily flowing. That's if the mass is not flowing, I'm going to use a U value. If it's flowing, I'm going to use an H value. There is a special case of constant pressure boundary work where I could use H's for a closed system. But otherwise, if you don't make it clear you understand why you're using H's for a closed system, it's either wrong or I'm going to count it wrong if you don't make it very clear why you're doing it. You should always use U's for a closed system, H's for flowing mass and the control volume, unless you have a very good reason to use something else. Um, that's an important point, and it's worth me saying two or three times. Okay. Now, if we simplify this a bit, if you look in the PowerPoint slides on lecture 11, the next thing it brings up after we get to the general first law for control volumes, the next thing it says is, what about if I've got for one inlet, we'll call him 1, and one outlet, we'll call him 2, or one inlet and one outlet. This actually can simplify a little bit, but we need to consider first the conservation of mass. Conservation of mass says, of course, if I add up all across all the inlets, the m dot, subtract across all of the outlets, the m dot, that's in minus out, and that's equal to the change dm d for the system dt with respect to time. If it's steady flow, that's going to 0. And if I've got one inlet and one outlet, this becomes m dot 1 minus m dot 2, then is equal to 0, which just means that m dot 1 is equal to m dot 2. And since they're both the same, there's really no reason to differentiate between the two. So it's a very common scenario I'm going to encounter where I've got a steady flow. Right, I've got a steady flow control volume with one inlet and one outlet. If that's the case, then the mass conservation simplifies just down to it's the same m dot. It's one m dot 1 at the inlet, m dot 2 at the outlet, and they are the same because it's steady flow. One has to equal the other, so we'll just call it m dot. If that's the case, then notice what we can do here, right? I only have one inlet. I don't have to add up all the inlets. And I've got m dot 1 coming in. I've got one outlet. I don't have to add up a bunch of outlets, and it's just m dot 2 coming out. And notice we can just call those both the same m dot. So for one inlet and one outlet, then the first law looks like this. So this is the conservation of mass. This is what the first law is going to happen with the first law. Q dot in, and I'm just going to write minus Q dot out, plus the power input. You can group these in any order you like, so long as you preserve the sign. So plus the power input minus the power output, plus then I'm going to take the energy of the mass in minus the energy of the mass out. But again, it's the same m dot. There's just one inlet, one outlet, and they have the same m dot between them. So it's just going to be m dot, the common m dot between them. And again, I'm going to add the in, subtract the out. I'm going to say that the inlet is 1 and the outlet is 2. So this is going to be H1 minus H2 plus V1 squared minus V2 squared, both over 2. You could add the G delta Z in here, or GZ1 minus Z2 in here if you really like. But again, we're assuming that GZ is negligible. So that's adding all the energies in, subtracting all the energies out, set that equal to 0. And a common question I will get is, hey, Steve, why is it 1 minus 2? Why isn't it 2 minus 1? Well, don't think about it as initial and final 1 and 2, that's normally what we use 1 and 2 to signify as initial and final. Understand that we're talking about the inlet 1 and the outlet 2, and the first law equation is always in minus out equals change. And I have the same thing here, in minus out equals change, in minus out equals change. If it's a steady flow control volume, the change is 0, so I just need to add my ins and subtract my outs. It's very common that we will have a device with one inlet, one outlet. And so this version of the first law will work just fine for that type of device. If I have a device where I have more than one inlet and or more than one outlet, I will need to use this version of the first law. And notice they're the same. I mean, I use this to derive that. So this is always correct. This is only correct if I've got one inlet, one outlet. Both of these only work if they're steady flow. Otherwise, this is a differential that I've got to deal with. meaning I've got to have some basic understanding of differential equations, which you guys will get there, but maybe you're not quite there yet. Okay, so I'm going to go back to then. So that's the kind of stuff I would be writing on these slides here, right? Yeah, so that's if I've got for steady flow control volumes with one inlet and one outlet. So that's what we just put on the document camera just a second ago. Okay, so let's keep moving on, shall we? Now, we're using 10th edition of Changle and Bowles Engineering Thermodynamics. Um, and for us, this is chapter 5 we're describing. In our text, there's going to be a section where it describes a number of very common steady flow devices. For us, that's section 5.4. And here's where I tell my students, hey, look, if you get, some people can read a textbook and get a lot out of it. Some people can read a textbook and not get much out of it. You do, as an engineer, you do want to learn how to be able to read really technical information and get the information you need out of it. That is always going to be the case. Engineering is the application of existing knowledge to solve problems. You're going to have to be able to gain new knowledge, meaning you're going to have to read technical information. So, reading a textbook is a good practice tool to do that. But I understand not everybody's going to get the same out of a textbook. But if you're not much of a textbook reader, this is the one time where I'm going to stomp my foot a little bit and say, you really, if you don't read anything else, read this section because you're going to get a problem statement that's going to say a heat exchanger with the refrigerant R134A in and air on the other side, and the hot stream and the cold stream is going to undergo these changes. And if you've read about what a heat exchanger is, and you've listened to me talk about what a heat exchanger is between those two, you're going to have some idea how to begin approaching that problem. So this is kind of one of those sections where I'm going to give you the quick crash course here over the next few minutes on these videos. But if you have read this material, and then I'm going to talk to you at least, I mean, the really simple basics is what I'm going to talk to you about, just enough we can start working some example problems. Hopefully between the two of those, you get a better understanding of what some of these common devices is. Because if I tell you, we have an adiabatic turbine with steam flowing through it, that immediately needs to bring up in your mind some picture of what that means. It doesn't have to be perfect, but you just want to be starting to think about what does that mean if I say I've got an adiabatic turbine? Let's talk about some of these common devices that we're going to encounter over the rest of the semester. All right, so we're going to introduce them in chapter 5, and we'll continue to experience them. Two devices that are very closely related. One is the idea of a nozzle. So if I draw the cross section of the nozzle, that's something that basically is tapering, where I've got mass coming in and mass going out. That would be a nozzle where it goes down to a smaller cross-sectional area at the outlet, where a diffuser is kind of the reverse of that. A diffuser would be where I've got mass coming in, and it's basically the reverse of a nozzle. It's going out into a larger cross-sectional area, right? And so if you understand that I've got m dot 1 is equal to m dot 2, which you could just call those both m dot, but I'm going to differentiate here because how do we find m dot? Well, it's going to be the density of the inlet, 1 coming in, times the area of the inlet, times the speed of the inlet is equal to the density at the outlet times the area of the outlet times the speed of the outlet. And you can see what's happening with both these devices. If we assume that the density is reasonably constant, right? If we assume the density is reasonably constant, it's not a great assumption with vapors. It's an okay assumption with liquids, but with vapors or gases, it's not a great assumption. But let's remove it from the equation. And so if I'm just left with AV is equal to AV, notice what happens when I change the area on one side. If A2 is smaller, if A2 is smaller like I have in the nozzle, if A2 is smaller, what does that mean for V2? Well, the product of all three of these has to equal the product of all three of these. And if A2 is smaller, that means density 2 and V2 both have to increase for this equation to hold true. All right. So if A2 is smaller, again, the product of rho 2 and V2 has to increase. And if rho 2 is very close to rho 1, that means V2 ends up taking the bulk of the increase. V2 has to increase. The same is true in the other direction. If the area increases, if A2 is larger, that normally means that V2 is going to be smaller, assuming the densities are pretty close. Right? Now, what happens basically, the nozzle, the goal of the nozzle is to increase the kinetic energy or the velocity of the fluid. A diffuser, you're going to end up decreasing that kinetic energy. And as a result, where does that energy go? Well, what it normally does is it manifests itself as an increase in pressure. A way you can kind of think about that is you've got all of this pressure stacking up behind this mass that starts moving slower and slower. You've got more and more mass trying to push its way in. That builds up a pressure as it encounters slower and slower mass coming out. So you decrease the speed. Well, that kinetic energy has to go somewhere. Where it goes is kind of an increase in pressure, which increases your enthalpy value. All right. So these are two devices that we will encounter, and then we'll look at the next one. And that's a nice place to start the next video.